First, I want to make announcement. So we have a poster session during the coffee break. So you're welcome to the poster session with the coffees, cookies, teas. Okay. So the first speaker is Professor Flavio Dickstein from University Federal of Rio de Janeiro. And he's going to speak finite-time blow-up for a complex Ginzburg-Landau equation.
Okay, thank you. Are you hearing me? Yes, I think so. Okay. First of all, I'd like to thank the organizer for the kind invitation. I would like also to say that I'm very glad to be here in Rio de Janeiro, like you. The difference is that I'll be staying here for the World Cup and you're not. But so the subject of my talk is this blow up for a special example of the complex Ginzburg-Landau equation. But okay, I'll start just to put it in perspective. I'll start with a simple ODE. So let me just consider, oh, okay. I think I have sent an update file, but this is an old one. So just forget lambda here is equal to 1. So just let me just consider V prime equals to V plus lambda times this nonlinear function. And I want to just to discuss the cases lambda equals to plus or minus 1. So in fact, okay, we see here that there are two mechanisms driving the solution V. There's this, I repeat, this is one. So this is a like a damping mechanism for the problem. And then you have this nonlinear forcing term, which with the sign minus is also a mechanism that driving the solution to 0. And with the plus sign, plus 1, and then this is a forcing term that is driving the solution to plus or minus infinity, but in any case to infinity. So this is, in the case of lambda equals to 1, there is a competition between these two mechanisms. Otherwise, the two mechanisms are driving the solution to 0. And in fact, with lambda equals to minus 1, all solutions are global and converge to 0. When lambda is equal to 1, then if V naught is small enough, in fact, absolute value of V naught less or equal than 1, then the solution is global. V equals to plus or minus 1 is a stationary solution. And then when V is greater in absolute value of than 1, then the solution goes to plus or minus infinity. Okay.
I'm sorry, is there a sign error in the equation?
No, this lambda here is 1. There's no lambda there.
There's no first lambda?
There's no first lambda.
No
I said, I'm sorry. Okay. So there's an error there. Okay. Okay. It's positive time. Yeah. Okay. So let me compare with the nonlinear heat equation. Then when we look at this equation here, perhaps you want to say that the picture is the same. We have a kind of damping operator, diffusion operator here. Then you have this nonlinear term. So that's the question. And the first answer is that, okay, if lambda is equal to minus 1 as expected, all solutions are global. And, okay, but the answer is no for lambda equals to 1, plus 1. And that's this famous example of Fujita, famous paper of Fujita of 66, that says that if alpha is small enough, smaller than or equal to 2 over n, then all positive solutions blow up. Okay, that's a little bit surprising, and well, perhaps when we think it twice, we would say, oh, perhaps this is not like a damping, because in fact there is no first eigenvalue for the Laplacian in the whole space, and then perhaps that explains the thing. Okay, that's one explanation, not the best one, but I won't discuss this. But anyway, it is also true that for large solutions, we have blowup. Large, for example, in this sense, you take any psi different from 0, you multiply it by S. If S is small, the solution blows up. If S is large, the solution, I'm sorry, if F is small, the solution is global. If F is large, then the solution blows up. That is true. And also, okay, if you consider the problem in a bounded domain with Dirichlet boundary condition, then you might say that this behaves like lambda u, in fact, okay, lambda 1 u, and in fact, this is true, so everything that we expect holds in this case. So the answer is yes for bounded domains. Now let us look at the Schrödinger equation. And when we look at the Schrödinger equation, then we see that, okay, the linear part, then we have, for the linear Schrödinger equation, we have a nice operator. The L2 norms, if we start with an initial value which is in L2, the L2 norm, for example, is conserved. So, of course, the solution is global. When you look at the nonlinear part, so just look at the ODE related to this problem. So also, you can put here plus or minus 1, solutions global also. So both mechanisms lead to global solutions. And in fact, when lambda is equal to minus 1, all solutions are global. And also when lambda is equal to plus 1 and alpha is small enough, less than 4 over n, also all solutions are global. However, when lambda is equal to 1 and alpha is greater or equal than 4 over n, it is still true that the solution is global if the initial value is small. However, when the initial value is large, in this previous sense, for example, then the solution blows up. So that's this strange thing that, in fact, when you look at the ODE, the only difference between plus or minus sign here is that the solution, in fact, the absolute value of the solution stays fixed. So the absolute value of the solution is constant. And so the solution is just turning. And turning to the left or turning to the right according to the plus or minus sign. But that makes a difference because for the Schrödinger equation, when it is turning one side, it does not blow up. And when it's turning in the other side, it may lead to blow up. Okay, that's the situation. So let me now consider this more involved equation, more complex equation. In fact, it's a complex equation. Z1, Z2, and Z3 are complex numbers. And that's the so-called generalized complex Ginzburg-Landau equation. This equation was proposed by those people. In fact, there are 3 papers that appeared more or less at the same time. In fact, those 2 papers here appear at the same number of the same journal, so the Journal of Fluid Mechanics in 1971. And those people were worried about instability of nonlinear flows. In fact, the emblematic problems of development of instabilities for the Poseo flow, for the Couette flow, Bernard problems, all kinds of these emblematic problems, and then they're trying to model to understand how instability may be generated, and they all propose the same kind of equation to model. The U here is the amplitude of the most unstable wave according to the linear theory. And, they all propose the same kind of type of equation to model this problem. And in fact, the Ginzburg-Landau equation also appears in many other contexts, like pattern formation problems, superconductivity, and others. So it became if you Google Ginzburg-Landau, you'll see a number of appearances which is comparable to nonlinear Schrödinger equation. Okay, but this is from the physical community, mostly. Okay. In any case, my question, I'm just looking the complex Ginzburg-Landau equation. This is another model where different mechanisms interfere, and I want to know if I can tell something about global and blowing up solution. I said but I just remember that I think I forgot to say that this work is in collaboration with Thierry Cazenave and Fred Weissler. Okay, so we've been interested we are still interested in answering those kind of questions for this equation. I'll tell you what we've been able to say for a particular case of the general problem. Okay. Let me just tell you some previous results about existence, well-posedness, and existence of global solutions. That there are some people that have been working on this problem. Great part of them are here, so you'll see by the names. So there are some works, but not too many works, even about the local and global existence of solutions. In the case, in the so-called defocusing case. So you saw that for the nonlinear Schrödinger equation, there's this strange behavior that if you're turning in one way, the solution might blow up, otherwise not. So this is explained as a kind of concentration of waves in some region. So this is the case where lambda equals 1. So the case leading to blow up is usually, I'll be calling this the focusing case, and the other case I'll be calling the defocusing case. So this is all in the so-called defocusing case. So Rio of Z3, perhaps it's better to write here the equation. I'll write the equation here. So that's Z3. So real part of Z3 negative means defocusing. And then there are some results about global existence of solution, but I'll not go into details. And there is, in fact, 2 results that I know, perhaps I would say 3, about blowing up solution of the general problem. One is, 2 papers first of all by Zag and then by Masmoudi Zag. In fact, they construct a particular blowing up solution. So with a particular profile, the profile is coming from a backward self-similar solution. So they've been able to construct one initial value for which the solution blows up. For some values in some region of the Z1, the Z2, Z3 plane. So this is for, by scaling, let me just assume that the real part of Z3 and the real part of Z2 is equal to 1. This is, okay, there's no loss of generality by doing this, but because I can always rescale the problem. So this means that this means that this is, of course, the focusing case. And then if the imaginary part of Z1 is Z2 obeys a certain inequality, then here they've been able to construct a blowing up solution. Yes?
The work of Constantine Turing company was considered theoretical condition.
Yeah, okay. I didn't mention that, in fact, here is with various results with for bounded domain, for the whole space with different boundary conditions. Yes?
The reason why I'm saying that
Yes.
is that if I'm in the theoretic boundary condition, the result of plot is trivial. If you take the homogeneous case, you have an ODE which goes up in finite time.
Okay, if you, okay, you can, you,
Then it's the Laplacian is 0, therefore you have the UT.
okay.
That goes up in finite time.
Okay. So let me say, I'm looking for solutions that are in LP spaces that are sub-overlapping in the whole space, but that are in LP. Of course, you can consider a constant solution, constant in space. Of course, yeah. Yeah. No, okay. I rephrase. I'm talking about blowing up solution in the whole space. Okay? Okay. In my whole lecture, okay, I'm talking about the Cauchy problem. Okay. So that's the question. Can we produce other solution than this one in the whole space? So that's a simple question, and in fact, to me, irritating question because you take a large initial value, as large as you want. Can you show at all that this solution blows up? I don't know how to do it in general. However, I'll show you how you can give a positive answer to this question in a special case, and that's the case where Z1 is equal to 0, so I'm forgetting the first order term, and and Z2 and Z3 are equal, and since they are equal, I can suppose that they're both unitary vectors. Okay. So let me consider now this problem, this Cauchy problem here, okay, where I have put Z1 and Z2 to the other side. Okay, so that's a problem that I want to consider. I'm sorry, this is supposed to be that, of course. Okay. But now I can view this problem as a family of problems parameterized by theta, and that goes from nonlinear Hero equation to Schrödinger equation. Okay. Theta equals to 0, we are in the heat case, and theta equals to pi over 2, we are in the Schrödinger case. Okay. And then I want to know what happens in between. Let me say that there is a great advantage of considering this particular problem is the fact that here we have a variational structure. So what's bad about the general problem, the general Ginzburg-Landau problem, is that there's no variational structure, so things are very difficult. Okay, now here, that's a way, perhaps you'll say that there's a mean way to get into a human situation where we have a variational structure, but that's the case. And in fact, we have an energy associated to the problem. This energy is the same, is independent of theta, so this is the same for all theta. And because if we define the usual energy here, the energy is it's non-increasing. In general, it's decreasing along the flow. And we know that we have the following results for negative energy solution. So if we start with an initial value with a negative energy, then we have blow up. First of all, always in the case of the heat equation, and that was proved by Levin in the whole space. And then there's this simpler argument of John Ball for bounded domains. And then for Schrödinger equation, for alpha greater or equal than 4 over n, and for finite variance solutions, Glassy in 77 proved that solutions blow up in this case. And then, okay, we were not aware, but in fact, in 2001, also there was this work of Snussi and Tayashi for the same problem that we consider here, showing that when the problem is close enough to the heat equation, then we have blow up. Okay? So when cosinus theta is large enough, so we're near heat equation, the heat case. Okay. Okay. Now, if we take our problem and we try to imitate the Ball's proof for the heat equation in the general case, we see that in bounded domain, for Dirichlet boundary condition, in bounded domains, the proof works fine. So we have blow up for negative energy solutions in bounded domains, and there's no reason why this would not be true in the whole space. But the proof doesn't work. And as you'll see, if you try to use Levin's argument in this case, we fall into this condition that seems to be technical, and in fact it is. Let me show you the first result. Is that, in fact, for any theta, negative energies leads to blow up. And in fact, that's the estimate of the maximal time of existence of the solution is bounded by this quantity. And let me also remark that this depends on 1 over cosinus theta, which means that when theta goes to pi over 2, this goes to plus infinity, because this is positive. And that's normal, that's expected, because we know that when theta equals to pi over 2 and alpha is smaller than 4 over n, all solutions are global. So we expect that this quantity goes to infinity when theta goes to pi over 2. And okay. And in fact, we can prove that when alpha is smaller than 4 over n, this is true, that the maximum time of existence of the solution, in fact, goes to plus infinity as 1 over cosinus theta. Okay. Well, that's technical, and I'll not giving you the proof, nothing about this result. Let me move on. And let me move on to a case which is more interesting. It's the case when alpha is greater or equal than 4 over n. Then, okay, we know that assuming finite variance, when alpha is greater or equal than 4 over n, then negative energy solutions blow up. And in fact, this finite variance assumption, which seems to be also to be technical, can be replaced can be dropped, but at the cost of being replaced by some other assumption. So if you are willing to admit that you are in the radial case and also that alpha is also smaller than or equal to 4. That strange number that appears here, but in fact, you can replace finite variance by this. And okay, in the proof of this result of Ogawa and Tsutsumi is just that, okay, you replace, instead of multiplying the equation by x squared and integrate and do some calculations, you just replace the solution by some, you multiply the equation by some phi of x, which looks like this, but it's bounded, so then you can do all your computation. Then you let this tail go to infinity and try to finish the proof. And then when you do this, it appears that you have to assume that the solution is radially symmetric, which from the proof is not very surprising, but also this strange condition that alpha must be smaller or equal than 4, okay? And now let me remark that, so we have tried to reproduce the argument of finite variance of the Schrödinger equation for this case. And it turns out that the situation is more complex, as you'll see, that because I'll discuss a little bit the proof. The situation is more involved in this case. And it turns out that exactly the same conditions appear even if you don't want to consider, even if you consider the finite variance, if you suppose that you assume that the solution has a finite variance, and even though there are some extra conditions that appear, and surprisingly enough, they are exactly the same conditions, even though they appear in a completely different way, but they are exactly the same restrictions here. So that's our third result that I would like to present. So negative energy, if you assume in addition that you are in the radial symmetric case and alpha is smaller than 4 for n greater or equal than 2, then the solution is uniformly, the blow-up time is uniformly bounded independently of theta. So that's like, that's morally like saying that for pi over 2, the solution blows up. Okay? That's the moral of the theorem. Okay. So since we're trying to prove something that is equivalent in some sense of the blowing up of the Schrödinger equation, it's natural that we try to use the same argument, which, by the way, is the only argument that, only existing argument for proving blow up for Schrödinger, for the Schrödinger equation. How much time do I have? 20 minutes. Okay. Okay. So I'm sorry. So okay, I didn't see. Let me. I have enough time to discuss a little bit about the proof of Theorem 1, and then I'll prove the Theorem 3. Okay. So let me show first of all the proof of Theorem 1, which is very simple. So let me prove that negative energy solutions lead to blow up for all theta smaller than pi over 2. So let me just observe that we have these two functionals related to the problem. First one, the energy E, and also this functional I. And they are related to the problem because the derivative of E of u of t is negative, is equal to minus this quantity, which is here. and also if you multiply the equation, so you multiply the equation by ut bar, you obtain this. In fact, the derivative of this equation. This is the integral form of the equation. And if you multiply the equation by u bar, you obtain this. So this is very simple. So I of u controls, minus I of u controls the growth of norm of u, norm L2 of u squared. Okay. Okay. And then let me just observe that, just forget about it. Let me just say that, okay, I is related to E by this, this is equality. This is negative. So I can say that I is greater or equal than this. I'm sorry. This is smaller or equal than this. I'm sorry. So minus I is greater or equal than this quantity. And then using this red here, and just forgetting this term, because this is also negative, then I can say that the derivative of u squared is greater or equal than this quantity. And so let me remark also that in particular for t greater than 1, let us suppose that the solution exists forever. Then for t greater than 1, this quantity here is greater or equal than a fixed quantity, because this grows a long time. Okay. So if I suppose that u exists forever, the L2 norm of u will go to plus infinity because of that. Okay. So let me move on. This is the inequality that I just have written before. Let me call f of t this quantity here. So this quantity here is f2 prime of t. This is f2 prime of t is greater or equal than this quantity. I'm just multiplying both sides by this f of t times this quantity here. And note that, in fact, what I've written here is just f of t. So I'm just multiplying both sides by the same quantity. And then this is Holder's inequality. And this comes from the fact that the derivative of norm of L2 squared is 2 times the real part of ut bar. Okay, so this is just simple inequality. And then what is here in the parentheses is just f2 prime. And then this is equal to this. Okay, so we have this inequality. Let me just for a moment forget about f prime of 0. So if we didn't have f prime of 0 here, we would have something like in constant f2 prime and greater or equal than f prime squared. And this is equivalent to saying that to some power is concave. So you take f to the power minus gamma, you take 2 derivatives of this, you obtain something like that. And in fact, the gamma is related to, this is equivalent to saying that this inequality holds. So in fact, one would obtain a contradiction by supposing that the solution exists forever. In this case, for the following reason, first of all, f goes to plus infinity, so that this goes to 0. So we cannot have a positive function that going to 0 and such that f to the power minus gamma is concave if gamma is positive. Okay. So if f goes to to infinity, f to the power minus gamma goes to 0. That cannot happen for a concave function. So, in fact, if we didn't have this, then we just need to check that this quantity here is greater than 1, and then that's why this condition found by Snus and Tayashi comes. Okay. Now, let me also remark that if I suppose that the solution is global, then as we saw before, f prime goes to plus infinity, and then at some time we may forget this quantity f prime of 0 because f prime of t goes to plus infinity, so we can replace this by some constant times f prime square, where this constant is as close as to 1 as we wish, and then that's all. Okay. Okay, so we look at this proof, and we got stuck for a moment with this proof because we didn't see how to remove the hypothesis that theta should be close enough to 0 here. But in fact, after a while, we notice that in fact we have to come to, if we come back to the equation, so u is not a general function, u satisfies the equation, so we come back to the equation and we multiply the equation by u bar, and then this quantity here is greater than I of u, because when you integrate, this is I of u. And then we see that, in fact, the integral of absolute value of u of t times absolute value of u bar is greater or equal than, not greater or equal than this quantity, which is just Holder's inequality, but in fact this quantity multiplied by 1 over 2 cosinus theta. So when you go to equation, we gain a factor here, and in fact when we plug this inequality in the previous computation, we obtain this instead of what we got before, and then that's the final of the proof, because that's the result. Okay. Let me just remark that when you look at this argument with a little detail, you can say the following thing. Oh, the blow-up time is in fact the time is related to the time where f prime of time is far away from f prime of 0. Once you are very far away from f prime of 0, then you can compute the blow-up time easily. And so, in fact, what we can prove, this argument shows the following result, is that the blow-up time is related to the time where u of t, in normal 2, is much greater than the initial L2 norm. So we look at the first time that the norm L2 norm of u of t reaches a certain k2 times u naught, so it's far away from for k2 greater than 1, and then we can estimate the blow-up time with the time where the L2 norm of u is large enough. Okay. So let me now go to the proof of Theorem 3, and the proof of Theorem is crucial in the proof of Theorem 3, the precedent remark. So instead of estimating the blow-up time, I will estimate the time where the solution is large enough in L2 norm. That's what I'll do. Okay. And so we estimate this quantity here, tau of the quantity tau. And so let me try to imitate the finite variance proof of Schrödinger equation. And let me assume that the solution has finite variance. So I'll multiply the equation by x squared. I integrate and I take the second derivative of the equation. We obtain this. This is equality. Okay. So let me remark that in the Schrödinger case, everything that is here is equal to 0, because cosinus theta is 0. Okay. So in fact, we have the following situation. So this is very simple. When n alpha is greater than 4, this is negative, this is negative. So the second derivative of a positive quantity is strictly negative. This cannot last forever. And so that's the proof for the Schrödinger equation. But here we have all this term here that we need to control. Okay, this term here is nice because it's negative, no problem. This is negative, this is positive. So that's that bad term to control. And this is not a problem, because in fact, since I'm estimating this quantity here, the L2 normal view is bounded. So this is when we integrate. When we integrate twice, I get this, and so the integral of over time of this quantity here is bounded by c times t. So you can incorporate in this first order term. It doesn't hurt you. So in fact, to finish the argument, we have to control this. That's the mean term here. Okay. Let me remark before going on that this coefficient, which is here, is smaller than 2, which is the coefficient that appears here. That will be important. Okay. So we have the following lemma. That's the end of the story. In fact, it's the proof of the following result, almost the end of the story, that we can control this quantity here by integral of the variance of the gradient, in fact, plus some constant times the integral of u to the power alpha plus 2 plus some constant, for solutions that are radially symmetric okay, given some ball in L2, you have this for some constant c. But for the proof of the lemma, that's where, in the proof of this lemma, that we have to suppose that this extra condition here, even if we are considering finite variance solutions. And this is sharp. This is sharp in the sense that if you, this is false for alpha greater than 4, and this is also false for non-radially symmetric solutions. So even if you're not considering radially symmetric functions, that's where these two conditions here appear. Okay. So let me assume the lemma. Then, in fact, we have, we have a positive term here, but as I said before, this can be controlled by this negative term here. It's the same term, but here we have a 2, and here we have a 1, and here we have a quantity which is smaller than 2, so this quantity which is here can be controlled by the negative quantity that is there. So in fact, we we are left with this quantity here, because there is a cosinus theta multiplying everything. So we have to control this. You have an integral over time, so we have to control this quantity. And, okay, that's much easier. We come back to the equation, and, okay, that's the relation involving I of u. So I of u satisfies this relation. And then we replace I by E. So this is all equality. And since this is positive, I just forget this. And then we have this inequality. We integrate over time, and we obtain this. And since we're supposing that, that t is smaller than tau, and up to tau, up to tau, the L2 norm is bounded. This is bounded. Okay, this is bounded by some quantity. And then when we put this into the variance inequality, we obtain this inequality. This is a negative coefficient, and this, of course, this is positive. This, of course, cannot last forever. And then this shows that this quantity tau is bounded, and so is the blow-up time. It's uniformly bounded. And that's it. That's what I had to say. Thank you.
So